Welcome to this exciting YouTube tutorial on Kirchhoff's voltage and current laws. Whether you are a student studying electrical engineering, a physics student, or just someone curious about how circuits work, you are in for a fascinating journey through the fundamental principles that govern the behavior of electrical circuits. Kirchhoff's laws are like the grammar rules of circuit analysis, allowing us to solve complex circuits and understand how circuits and voltage flow in intricate systems. In this tutorial, I will take a deep dive into two powerful laws. Kirchhoff's current law, also known as the KCL, is all about the conservation of electric charge at any point in a circuit. We will explore how to apply this law to determine current distribution in parallel and series components. The Kirchhoff's voltage law. This is also known as the KVL, or let me say abbreviated as KVL, and it is based on the principle of energy conservation in a closed loop of a circuit. We will see how to use this law to analyze voltage drops across resistors, batteries, and other elements in a circuit. By the end of this tutorial, you will have a solid understanding of these laws and how to use them to analyze various circuit configurations. We will break down simple concepts, complex concepts into simple, easy to understand explanations, and we will walk through practical examples step by step. Whether you are preparing for an exam, you are working on a circuit project, or just expanding your knowledge of electronics, mastering Kirchhoff's laws is an essential skill that will serve you well on your journey into the world of electrical circuits. So grab your notepad, fire up your curiosity, and let's dive into the fascinating world of Kirchhoff's voltage and current laws. Right, so I'll go first by explaining some terms that we'll be using in this KCL and KVL, and there are terms that should be known in electrical engineering. There are terms that is very popular. You use it everywhere, and in almost all courses you take, or maybe in almost all things you meet in electrical engineering. So we have nodes. We have paths, we have loops, and we have branches. So these four terms are used everywhere, are used virtually everywhere in electrical engineering, because we must be able to identify the nodes in electrical circuits. We must be able to identify the paths in which current flows through. We're able to identify loops, and we're able to identify branches. So basically, what's a node? A node is a point at which two or more elements have a common connection. That is, whenever we have a place in which two or more elements have a common connection, is called a node. For example, let's say this is a resistor, this is an inductor, right? This is a resistor. So when these two elements meet, the point in between these two elements is called a node. Whether they are two or they are three, let's say there's a capacitor here, or let's say there's another resistor here. So this point is known as a node. So at that point at which there's a common connection between two or more circuit elements is called a node. It's called a node. So what is a path? So the set of nodes and elements that we have passed through is called a path. So a path is usually a set of elements. For example, we have let's say we have a circuit. This is a resistor, right? And we have another resistor. Then maybe we have a source here, and we'll come back and to let's say the circuit ends here, or maybe the circuit continues and we have some other networks here. So from this point to this point is called a path. this point to this point is another path. So as long as it contains one or two elements, it is called a path, and as long as current is passing through it, it is called a path. So a path is just a means or a way in which current can pass through. Set of nodes, elements. For a particular circuit to be called a path, it must contain circuit elements. It must contain circuit elements, right? At least one circuit element. So I can even say that this is a path, because as long as I know that it's a part of a circuit element, so it means that current will also pass through from this end to this end. So it's still a path for current to pass through. So that is called a path. And if the node if the node at which it started is the same as the node at which we ended, the path is called a loop. So for example, let's say at this end here, and it is joined to this end. So because the node at which the path started, it is the same node at which it ended, so it is called a loop. It is called a loop, right? So in a circuit, when you trace in a circuit or in an electrical network, when you trace a node and you see that there's a path at which you can come back to the same node, so that path is called a loop. And the last one is a branch. A branch is a single path in a network. It's composed of one simple element and the node at each end of that element. So it is usually a single path in a network, and it's composed of one simple element and the node. So those are the four terms we'll be using in Kirchhoff's current law and voltage law. Especially in Kirchhoff's current law, we'll be using nodes, and in Kirchhoff's voltage law, we'll be using loops. So let's go straight forward into Kirchhoff's current law and Kirchhoff's voltage law. So the Kirchhoff's current law states that the algebraic sum of the current entering any node is 0. So this is very, very straightforward. So in a particular electrical circuit, let me define a node. Let's say this is a node, right? This is a path, right? This is a path, this is another path, this is another path, this is another path, and this is the node here, right? So I will call this current IA. I will call this current IB. I will call this current IC. And I'll call this current ID. So basically, what Kirchhoff's current law is saying is that the algebraic sum of the current entering a node, it is 0. Note the word entering. That is, we are looking for the sum of the current entering a node. So which means that if it is not entering a node, it will not be a sum, it will be a subtraction. Right? So look at this node here. You can see that there are two currents that are entering the node, which is IA and IB, and two currents that are leaving the node, IC and ID. So for us to make IC and ID to be entering the node, what do we have to reverse the direction, right? So reversing the direction will make them carry a negative sign. So if you have to take the algebraic sum, what will it be? It will be IA plus IB plus minus IC, because we have to reverse the direction. We want you to be entering the node, plus minus ID is equals to 0. So, and by this, I can bring IC and ID to the other side and say that we have IA plus IB to be equals to IC plus ID. I'm very sure you guys are following me. So that is the simple explanation of Kirchhoff's current law. It's a very, very simple law, and it is used in various topics in electrical engineering. It is used in various concepts in electrical engineering. So we'll look at an example that will explain so many things about this KCL, how we apply this KCL in circuit, how we use it in simple circuits or simple node circuits, and also in complex circuits. Okay, let's do this example. This is the example we will be using to explain KCL. There will still be another example that will explain comprehensively KCL, and it will be a complex circuit more than this. Okay, so the question here is let us count the number of nodes that are in this circuit. We want to count the number of nodes and the number of branches in this circuit. So from our explanation that a node is a point of common connection between two or more elements in a circuit, right? So if I'm to count a node here, this is a circuit element, this is another circuit element, right? So there's a node here, which is node 1. That's node 1. There's a node here, which is node 2, because this is also in between a circuit element and another circuit element. So there's another node here, which is node 3. There's no the node here is also same thing as the node here. Why? Because there's no circuit element in between them. So we usually call them single node pair. Single node pair circuits, right? So whenever you have two places in which two parts are joining together, but you can see that when the two parts join together, there's no node in between the adjoining parts, right? There's no circuit element in between the adjoining parts. So this point here and this point, they are the same node. So you can see that they are a pair. So we call them a single node pair. So it is just one node. Same thing as this point here and this point here. So we can count it as a node, but it's the same node as this node on the other side. So we call these two single node pairs. So the number of nodes in this circuit is 3. We have 3 nodes. So what are branches? So basically what I used to explain to students is that the number of branches is the number of circuit elements you have in that circuit. It's just as straightforward as that. Because what does a branch mean? A branch is a single part in a network. So this circuit element is a part. Current is flowing through. This is a part. This circuit element here too is a part. And this is 5 ohms. This source here too is a part, and this 80 volt is also a part. So basically your number of branches is the number of circuit elements you have in that network. So how many circuit elements we have here? We have 1, 2, 3, 4, 5. So basically we have 5 branches. So the next thing we want to do is that this 18 volts, it supplies 8 amperes of current, right? It supplies 8 ampere current. And what is the value of RA? I want to get the value of RA. I will be using KCL to get the value of RA. So look at it. There's a node on top. This node here and this node here, there is just one node. So we're taking it as just one node. So at a particular node, KCL is happening. Because what does KCL? KCL means that the sum of current entering a node must be, the algebraic sum of current entering a node must be equals to 0. Am I right? So if they must be equals to 0, it means that we can, for us to get the current flowing through the resistor RA, let's say the current is going this way, and let me call it IA, we have to take the KCL at this upper node. So that is straightforward, right? We have 4 branches that are connected to this upper node, which is the 18 volts, this branch here, and this branch here. So if you take the KCL, you got 8 amperes is entering. So 8 amperes is entering. The 30 amperes is also entering, plus 13 amperes then the Ix is going out, so Ix then plus Ia that we are looking for. Kirchhoff's current law states that the algebraic sum of current entering a node is equals to 0. So indirectly it means that the sum of current entering a node is equals to the sum of current leaving a node. So we have two currents leaving the node, Ia and Ix, and we have two currents entering the node, 8 amperes and 13 amperes. So what do we have? We have 21 is equals to Ix plus Ia, right? So we now need to get what Ix is. So there's something about parallel combination and series combination. So when elements are connected in parallel, they have the same voltage. So if I want to get the current Ix, by Ohm's law states that the voltage is directly proportional to the current. So which means that V is equals to IR, right? And for me to get Ix, it will be what? V over R. So that will give me 18 over 6, which is equals to 3 amperes. And therefore I will have 21 is equals to 3 plus Ia. And therefore Ia will be equals to 18 amperes, which is 21 minus 3. Alright, so we've gotten Ia. So the next thing for us to get is Ra. From back to Ohm's law. Ohm's law states that the voltage applied is directly proportional to the current flowing through a conductor. So which means that for me to get R will be equals to V over I. What is our voltage? Voltage is still 18 volts divided by, and our Ia is what? 18 amperes. And therefore Ra is equals to 1 ohm, and that is our answer. So I think you can understand right now how KCL, Kirchhoff's current law, can be used to analyze a circuit. It is very, very simple. Look at a node, count the number of nodes, then at your object of interest, look at the node that is connected to your object of interest, and of course take KCL at the node near to it. KCL states that the algebraic sum of current entering a node is equals to the sum of current leaving a node, and that is straightforward. And you can just go on and apply the equation and get the value you are looking for, get the variable you are looking for. That is very, very simple. So before we solve the a bigger circuit than this, let's talk about Kirchhoff's voltage law. So Kirchhoff's voltage law states that the algebraic sum of voltages around any closed path is 0. So look at the comparison between KVL and KCL. KCL is the algebraic sum of all currents entering a node. KCL, node. KVL, path. So that's why it is very necessary for you to understand the difference between node, paths, loops, and branches. So KCL states that the algebraic sum of current entering a node is equals to 0, basically saying that the algebraic sum of current entering a node is equals to algebraic sum of current leaving a node. KVL states that the algebraic sum of voltages in any closed path. So when we say a path is closed, when a path is closed, it means that when the node where current enters is the node, a path, the beginning node is also the ending node. So that is a closed path. So in a path, when the beginning node of a path is the same thing as the ending node of that path, it is known as a closed path. It is known as a closed path. So the algebraic sum of voltages around any closed path is 0, and which means that if we have something like this, let's say this is just a circuit element, this is another circuit element, and this is another circuit element, Then we have this, we have V1, right? We have V2 and we have V3. So this is just a circuit there. Then for us to take the KVL around it, this is a path. You can see that, let's say this is a node here. When we go through this path and come back, we still go back to the same node. That's a closed path. So the sum of the voltages around any closed path is 0. So let's start by moving clockwise. Let's move clockwise. So right, when we move clockwise, we will have V2, right, minus V3, because when we enter this, when we are going clockwise, we enter through the negative terminal. So that's why it has minus V3. Then when we come here, we still enter through the negative terminal, right? So that's why it will have minus V1. Then that's all. We came back to the beginning node, so it's equals to 0. So what does that mean? It means that V1, we can say it means that V1 is equals to V2 minus V3, or we can say that V2 is equals to V1 plus V3. So it's really depending on what the question wants us to do. So let's do an example. Let's do an example on that. So in this circuit right here, we want to get Vx, and of course we want to get Ix. Ix is what the current going through this resistor. So, and of course I will be going clockwise, and I'll name the current moving clockwise Ix. Right, so we want to get Vx. Find Vx and Ix. Applying KVL, what do we have? So when I enter this source here, it enters through the negative, right? So I'll be having minus 7. Then when I enter this resistor here, I'll having plus Vx. And when I come here, I'll have minus 5, which is equals to 0. That's what KVL says. So what does this mean? It means that Vx is equals to 7 plus 5, which is equals to 12 volts. We've gotten Vx. So how do we get Ix? We use Ohm's law. Use Ohm's law. So at that resistor there, a resistor always obey Ohm's law. It obeys Ohm's law. So, and by that we know that the voltage on the 100 ohms is what? 12 volts. And we want to get the current. So what does that mean? V is equals to IR. That is Ohm's law. So which means that Ix will be equals to Vx over 100. That is, the resistance is 100. So Vx is 12, and we divide it by 100, and therefore we know that Ix is equals to 0.12 amperes, and that is our answer. And I'm very sure that we all understand what I just did. So this is a basic example of how to apply KVL and KCL. So let's take this bigger circuit and we'll use the application of KCL and also KVL to get the object of interest. This is the circuit we'll be analyzing to explain KVL and KCL broadly. Right, so we can see that we want to get Vx. This is Vx here. We want to get Vx, that is the voltage on the current source. We want to get Vx, that is find Vx. So for us to do this, we need to analyze the circuit to get Vx, and we're going to do that using KCL and KVL. So we can say let's locate the nodes on this circuit. So there's a node here, and there's another node here, and like I explained that these two nodes are single node pair circuits. They are single node pair circuits. And because why? Because there's no circuit elements in between them, and therefore we usually refer them as a single node per circuit. This is a node. Both of them are nodes, but they are the same node. It's a pair that is acting as just one node. Yes, and of course there's a node here too. There's a node here, and basically if we are to count the number of nodes in this circuit, we'll say that there are 4 nodes in this electrical network. There are 4 nodes in this circuit. So at this node, I can write a simple KCL equation, right? The sum of current entering is equal to sum of current going out. So what would that be? It means that I4 plus IX is equals to I2. Is equals to I2. That is an equation. So, and you can see that these 3 quantities, these 3 variables that we have here, we don't have any definition for them. We don't know any one of them. We don't know the value of any one of them, and that presents a problem to us, right? So, but we can get them using another way, right? So let's write KVL equations. This first loop, a loop is a closed path. So at this first loop, let me name this one as 1. I'll name this one as 2. Right? So at this first loop, how will I write the equation? Right? So I'll write it as what? Minus 60. I'm going clockwise, plus V8 plus V10 is equals to 0. Minus 60 plus 0. So what does that mean? It means that V8 plus V10 is equals to 60. So that's an equation. Applying KVL to the second loop, we have what? We have V4 plus V4, right? I'm going clockwise. So the voltage on these 2 ohm, I was saying in the last example that when 2 elements are connected in parallel, like I said, 2 elements, I didn't say just 2 resistors. Whether they are resistors, whether they are not resistors, whenever they are connected in parallel, they will have the same voltage. The same voltage will be dropped in each of the elements. It will be dropped in each of the elements, and therefore you can say that the voltage on this current source, which is Ix, the Vx here is the same voltage on 2 ohms. So what do we have? We have plus Vx, then minus V10 is equals to 0, right? So, and therefore this is becoming very straightforward to get. If you look at it, you can see that we can get V8. Look at V8 here. V8 has 5 ampere going into an 8 ohm resistor. So by Ohm's law, V is equals to IR. What do we have? V8 will be equals to 5 multiplied by 8, which is equals to 40. So wherefore we know that V8 is equals to 40 volts. So from, let me say this is equation 1 and this is equation 2. So from equation 1, we can say that V10 is equals to 60 minus V8, and therefore V10 will be equals to 60 minus 40, which is equals to 20 volts. So I know what V8 is, I know what V10 is. So therefore, from this equation 2, I can get my answer. So V4 plus Vx is equals to V10. And what is V10? 20, which is equals to 20 volts. Am I right? So, and therefore I can say that Vx what is equals to 20 minus V4. So therefore we need to know what V4 is. And of course, we can also use and we can also use KCL in this situation. That is because if you can determine V4, we can get Vx, and therefore using Ohm's law we can get Ix. Okay, at this upper node here, we can use KCL to get I4. We can see that 3 branches are connected to the node, right? 3 branches are connected to the node, and therefore we can get I4. So using KCL at that point, we know that 5 ampere is entering, right? Others are going out. I4 is going out. I4 plus I10 is also going out. I10. And of course, you can know that we know that V4 is I4 is what? Using Ohm's law, it will be V4 over 4 ohms, right? So using the new board, we have Vx is equals to 20 minus V4, right? And of course, we know that by KCL, 5 amperes will be equals to I4 plus I10. And if you use Ohm's law to get the definition for I4 and I10, we'll be having V4 over 4 ohms plus V10 over 10 ohms, right? So, and we need to get what V4 is. So we got V10 as 20 volts. So what do we have? We have 5 is equals to V4 over 4 plus 20 over 10. So that gives us 5 is equals to V4 over 4 plus 2. So that straight gives us V4 over 4 is equals to 5 minus 2, which is 3. And therefore V4 will be equals to 12. And therefore V4 will be equals to 12 volts. But we are looking for Vx, and in the equation I wrote in the former board is that Vx is equals to what? 20 minus V4, and therefore will be what? 20 minus 12, which will be equals to 8 volts. So right now you can see how we used KVL and KCL to analyze a circuit. By the way, this equation we use here, 5 is equals to I4 plus I10, that I wrote in the former board, is KCL. Like I explained, 5 is going in, I4 and I10 are going out of the node, right? So you can see how we use KCL and KVL to analyze a circuit. And it is very, very simple. Be very, very sure of what you are doing. Take a node, get KCL at that node, take a loop, get KVL at that node, and check your equations, how you can solve the simultaneous equations you are getting. And that's just it. And of course, sometimes you'll be applying Ohm's law. Ohm's law is a very, very simple law, and it states that the voltage applied to a conductor is directly proportional to the current going through it, and that's just straightforward. So that is very, very simple, and I'll leave you with that for now. Thank you very, very much for watching this tutorial, and in the next lesson we'll be treating some other topics that will make your electrical engineering journey very, very smooth. Thank you very much.